About the EMF equation of three-phase alternator or synchronous generator. Normally the EMF equation in the sense, while we are giving the rotor input, like mechanical energy we are giving into the generator rotor shaft, so that through the drive pulley systems or any of turbine we connected directly. So whatever input, mechanical input you are giving in the rotor also having the winding and stator also having the winding, armature winding and field winding. So the field winding getting rotated, so the generated EMF, it can be the electromagnetic field cuts in the stator conductor. So there the induced EMF that had been generated in the stator, that we are getting in the output of the generator, three-phase output. Okay. So while you are based on that generated EMF, so we are going to derive the expression, that is the EMF equation. Why we are called as the EMF equation? Because here, while you are giving the input, the EMF was the major role, electromagnetic force, right? So while you are giving the rotor input, so the EMF has been induced in the stator, that we are collecting in the output potential. So that how it is induced EMF has been generated, how the pole is formed, what are the various factors considered. Through that we are deriving the EMF equation. So you see here, that was the basic fundamental notations. The P is the number of poles and pi is the flux per pole, okay, in Weber. Then N is the rotor speed in RPM, okay. So here only the rotor speed, here only we are giving the mechanical input, that we are allotted the notation capital N, that is the speed of the rotor in RPM, that is the revolution per minute, okay. How it is rotated, how many revolution rotated per minute, that is the speed, okay. Here the frequency in hertz, okay, because we are having here the alternator, that is the three-phase AC supply. So here the frequency will be there. So you all know that is the sinusoidal wave, right? So the pure sine wave. Okay, if you are in the three-phase, that is a single phase. If it is you are the three-phase, so the three-phase waveform you all know like this. So that is the RYB. Okay, so here it is have the frequency. That is the variation of the frequency. That is the 50 hertz. Then total number of conductors which is used in the stator, both the stator and rotor winding, and number of turns per phase. What is the difference between the conductors and the turns? The conductor is the single line, single conductor. We can single line of wire or single conductor, single trans. That is while you are making the winding, it is the turn, okay. That is the turn. If it is a conductor, we can consider the single line. Turns in the sense we can group the conductor together, and how many turns are used in the particular coil, okay. That is the turns per phase, okay. The T is the number of coils, that is the turns per phase. This is all the basic notation, you should remember it. Based on that we are going to derive, or we are going to find the EMF equation of the three-phase alternator. You see that is the flux per pole. Initially while you are giving the mechanical input to the rotor, the flux it is generated, that was the origin. So that is how many flux, how much quantity of flux has been generated per revolution, that is the differential flux. That is a small amount of flux has been generated in the one revolution. So that is the differential flux d pi. That should be equal to number of poles into flux. Number of poles in the sense, here we are having the poles, maybe the 4 or 8 or 6, whatever it is. So number of poles, the poles in the sense nothing but it is combination of or collection of conductors grouped together to form any poles, right? So either north pole and south pole, here the poles into flux. So the next thing here, it is the you are giving the mechanical input up to the what time you are giving, what is the total time period. So here the differential time, that is the time taken to complete one revolution, so that is the 60 by n. The revolution per minute, that is the speed. So 60 is the seconds per minute, okay. 60 divided by n. So the EMF per conductor, that is the both you can divide it, how much EMF has been induced per conductor, that is the differential flux with respect to the differential time. How many time, what is the total time you are given the input, mechanical input. So the P pi into n divided by 60. How it is came? Because you can consider the both d pi is the P pi divided by 60 by n. So last denominator can multiply it with the first numerator. So P pi n divided by 60. So that is the EMF per conductor. So the EMF per phase, EMF per phase per conductor is different. Per phase in the sense you need to consider the total conductor. So EMF per conductor into total number of conductor. So here already EMF per phase, EMF per conductor we found it into the total number of conductor, that is the Z we assumed here, because EMF per conductor we found it. What is the total number of conductor in the alternator? So you need to find the total EMF. So you need to consider the total conductor, right? So EMF per conductor into total conductor you add it, that is the EMF per phase. But we all know the formula for the speed of the rotor, that is the N it should be, that is the, we can put Ns also, that is the synchronous speed. Ns it should be equal to 120 F by P. So you can replace that Ns is the synchronous speed, that is the speed, actual rotor speed. So here you can replace the, instead of N you can replace the 120 F by P. So instead of N I replaced here 120 F by P. So here it is the both the side the P is there, so number of poles it is getting cancelled, and here the 120, here 60 you can eliminate, and finally you can find the 2 F pi into Z, that is the EMF per phase. Okay, but we know the general formula, the total number of conductor it should be equal 2 into turns per phase, that is the actual formula for the Z. Okay, total number of conductor it should be equal to the twice the turns per the phase. Okay, so the 2t, so you can replace it in terms of Z into 2t, so you can 4f pi into t. Okay, that is the EMF per phase, actual EMF per phase equation. But we all know that form factor it should be equal to the RMS value by average value. Why you should consider the form factor? Because we have the sinusoidal waveform here. For the sinusoidal waveform, the form factor it should be the RMS value by average value, that should be equal to 1.11. Okay, you all studied in the circuit theory itself. So the form factor for the sinusoidal wave, because here the output is the sinusoidal wave. So the form factor RMS value by average value, the sinusoidal wave, the form factor value is 1.11. So you need to multiply it with the EMF per phase. So you can multiply it with the EMF per phase. So 1.11 into, actually already we found it 4 into F into pi into T. So you can multiply it here 4.44 F into pi into T. That is the actual equation. If you want to change the expression in terms of T or Z, we know the relationship between the T and Z. If you want, both are, it should be the same. If you are added the winding factors, right? If you are added the winding factor like distribution factor and the pitch factor. Okay, sometimes the pitch factor we can call it, we can notate it instead of Kp or Kc, the both are the same. That is the Kw is the winding factor. If you are consider the winding factor here, it is the winding factor, it is always the less than unity. So that is the 4.44 into, you can add it Kp into Kd, that is the pitch factor, this is the distribution factor. So here the F into pi into T. Okay, why you should consider the winding factor and the distribution factor, pitch factor and distribution factor? It is also very close related to the generated EMF. While we are deriving the expression of pitch factor and distribution factor, it is, you can see the expression, it is related to the generated EMF. Okay, we are deriving the EMF equation, so that you can consider both winding factor. The winding factor, that is the Kw, it should be equal to the product of pitch factor and the distribution factor, that you can replace it here. So the EMF equation, it should be equal 2.22 Kw into F pi Z. Okay, if you are putting Z here, 2.22 it may come, or if you are putting T, what it will come? That is the 4.44 Kw pi, F into pi into T. If you are put it the T here, the T it should be equal, what it will come? Z by 2. Suppose if you are put it Z, you can, if you are put it the Z, yeah, 2.22 it may come. If you are added the T, here the 4.44 it will come. That is the actual expression of the EMF equation. You should consider these all primary factors, that is the, this all notation you should remember. Based on that, here you are consider the one revolution, then one conductor, then conductor per phase, then form factor, then final winding and this winding factor. At the final expression, that is the EMF equation, it should be equal EMF equation E phase or E, it should be equal 4.44 into kW into F pi and T. That is the final EMF equation of the 3-phase alternator. If you have doubt, you may ask now. Okay, thank you.